Welcome back, and welcome to the second example of creating a system of linear equations and solving them. This is a very similar but more complicated example of the children's age puzzle. I have Roland, Steve, and Tessa are siblings, and I know the following 3 bits of information. That together the boys are as old as Tessa. Next year, Tessa will be half as old as the sum of Roland's age plus 3 times Steve's age, and 3 times Roland's age is 4 less than 5 times Tessa's age, minus 7 times Steve's age. These sentences are kind of complicated, so I want you to take a moment to parse them and think about how these can be translated into linear equations. Alright, we're back. So let's see what we can do. First off, we're going to use variables to represent the ages of the children. Let's use R, S, and T as variables for Roland, Steve, and Tessa's ages, respectively. This first constraint isn't terribly hard to say, that the 2 boys are as old as Tessa. It means that the sum of their ages is equal to Tessa's age, which means that R plus S is equal to T. This other one is slightly more complicated. It says that next year I have something that will hold, which means that I need to consider essentially their ages are all added by 1, and then I have all these other coefficients that go on. So next year, Tessa will be half as old as this phrase. Well, saying Tessa's age is half as much as this is the same as saying twice Tessa's age is equal to these things. That twice Tessa's age in a year is what we're going to start with. So twice Tessa's age in a year is equal to Roland's age in a year plus 3 times Steve's age in a year. Right? We have these plus 1s, but when I take this multiple of 3, I need to make sure it's by the quantity s plus 1, because it's 3 times what Steve's age will be next year. We'll go through and simplify this later once we've erased the sentences. This last one is that 3 times Roland's age is 4 less than 5 times Tessa's age minus 7 times Steve's age. Well, first I'm going to have a 3 times Roland's age is on one side. So one side is 3 times Roland's age. On the other side, I know I'll have a 5 times Tessa's age minus a 7 times Steve's age. And finally, I have to deal with this 4 less. 4 less, I'm thinking of that this side is 4 less than what I've written down so far, so I need a minus 4 right here. So we have these complicated sentences, but we've kind of phrased them in terms of linear algebra, linear equations, that we definitely know how they work. So let's erase the sentences and deal with algebraic simplification. Okay, now we're back. This first one is rather simple. However, we want to format it in such a way that all of our variables are on the left-hand side and we only have a constant on the right-hand side, which means I need to subtract both sides by t. So that means I have r plus s minus t is equal to 0. That is equivalent to this equation, so I'm going to erase this equation. For this one, I have all these different quantifiers. I want to expand by distributing across the parentheses, and then I want to group like terms together, and I want to do the same thing of splitting it to the left-hand side. So watch as I go step by step up this way. Okay, I followed the following steps. First, all I did was distribute across the parentheses, and I left all the terms separate. Then on each side I combined like terms. Specifically, the plus 1 and the plus 3 became a plus 4. But now all I'm doing is taking all the variables and moving them to the left, and all the constants and moving them to the right. So I subtracted by r and minus 3s, and I subtracted by 2 on both sides. And so what I see is I have a minus r minus 3s plus 2t equals 2. And that's our value here. So now I can erase all of this work, and I can focus on this equation here. When I look at this equation, I've already got everything simplified and combined. So all I need to do is move things over to the other side. Specifically, I need to subtract 5t and add 7s, and I will have what I want. We see that this equation here is equivalent to this equation, and it's formatted in the right way, that I have my variables all on the left-hand side. I've matched up my columns to match the different variables, and on the right-hand side, I've got the constant values. So I'm going to erase this equation. Now let's go through and think about how we can solve this set of equations. The first method is, remember, the graphical method. Well, unless you can carefully draw planes in 3-space, or think about that in your head, this is going to be a difficult problem. So I don't recommend thinking about 3-dimensional things. Let's skip the graphical method. It won't be helpful at this point. So now there's 2 more methods left. There's substitution, and then there's adding up the equations. So let's focus on the substitution by saying let's try to find an equation by solving each variable at a time. Let's start here and see that what I have is that I can actually phrase this in terms of t equals the other 2 variables. So with this, we see that if I just add t to both the other side and then swap the sides, I have that t is equal to r plus s. Which means that I can take any instance of t in the other equations and replace that t with r plus s. And that will give me a new equation. So let's start by taking that and substituting into this second equation. It's important when doing the substitution that you make sure to group the terms correctly. That is, when I have a 2 times t, I need to multiply this 2 by everything t is equal to. So when I have 2 times the quantity r plus s, I've grouped them together. And now we can take this and we can expand, distribute, and group by like terms. So I'll distribute the 2 across the r plus s, and then group the terms in with the r and the s here. So now we have, from this equation, by grouping like terms, we have this equation. R minus s is equal to 2. But this means that we can phrase s in terms of r, if we would like, by solving. I will add s to the other side, subtract 2 from both sides, and we'll find out. Now we have found out that s is equal to r minus 2. So we see that s is equal to r minus 2, in addition to t being r plus s. Which means that if we take these 2 substitutions, we can plug them in to this equation. We have one more equation left that we haven't used. But one thing we want to do is we want to make sure that this is entirely in terms of one variable when we're done. So what I want to do is I want to do this substitution up here first so that t is phrased entirely in terms of r. So let's make that change here. So by substituting s for r minus 2, I see that I can group them and get that t is equal to 2r minus 2. So I'll perform this substitution and this substitution onto this equation. After performing those substitutions, we see that we actually have this equation now. And now what we need to do is we need to distribute and combine like terms. For distributing, I see that I have 3r plus 7r minus 14 minus 10r plus 10 equals negative 4. Let's now combine like terms. When we combine like terms, we find out we have 3 plus 7 minus 10. Those are all the coefficients of the r variable. And we have a negative 14 plus a 10, and equals a negative 4. But when we look at these terms, this is 0 times r. And when we look at these terms, we see we have a negative 4. So in the end, what happens is, this equation, as we go through, we find a true fact. Negative 4 equals negative 4. This holds no matter what the value of r is. So this equation is already implied to hold because we have negative 4 equals negative 4, and we have these 2 substitutions. Therefore, r is a free variable. We can let r have any value we want, and then we get a value of t and s from that. Which means we have an infinite number of solutions. We have an infinite number of solutions, but let's fully describe the solution set. Now our full solution set is that r is free, so we can take any real value, and s is equal to r minus 2, and t is equal to 2r minus 2. So once we know Roland's age, we know Steve and Tessa's ages as well. Now one thing to keep in mind, because of the context of the problem, not because of the equations we put, but because of the context of the problem, these people do not have negative ages. So r is not really free, it can't be negative 10. So it should be at least 0, but so should s and t. So if s is at least 0, then r is at least 2. And if t is at least 0, then r is at least 1. So we see that the lower bounds on r is actually meaning that, well, at least as long as r is at least 2, as long as Roland's at least 2 years old, there is a feasible amount of ages for Steve and Tessa. That said, all of these things are not that are satisfied. Always, Steve will be 2 years less than Roland, but Tessa, as Roland ages, was growing twice as fast. It's not so. This isn't something that can hold all the time, but it can hold at certain instances. Of course, having R be 1,000 isn't technically incorrect, but it's probably not really very feasible. Specifically, really what we're saying is that this puzzle is ill-defined, that there are an infinite number of solutions, and so therefore you shouldn't feel bad that you can't find exactly what these kids' ages are. But let's take a minute to figure out exactly what happened here. We did the substitution method, and we found out that the T and S depend on R, but R does not depend on anything. We could have done it in a different order and gotten S doesn't depend on anything, and then R depends on S. But let's get a better feeling by using the addition of equations and just do some equation arithmetic to discover some of the reasons why this happened. So let's go back to our original equations. So these are our original 3 equations. Now one thing that happens is that we know that for any feasible age for Roland, Steve, and Tessa, that these equations do hold. So for each equation, the left-hand side always equals the right-hand side. So if I do the same trick, if I do the same arithmetic or algebraic manipulation to the left-hand side as I do the right-hand side, I will get a new legitimate equation. If I combine 2 equations in some way, I will get a new equation that works. So I'm going to start listing new equations, and we'll discover something new. And the way I'm going to do this is I'm going to say, well, look, I can take the 2 that's here. If I multiply it by -2, I will get a -4. And therefore, I can somehow get this right-hand side to cancel out with this right-hand side. So I'm going to modify this equation by performing a manipulation by multiplying by -2. So by multiplying this entire equation by -2, both sides, I get a new valid equation. 2r plus 6s minus 4t equals -4. Now what I'd like to see is see if this -4 and -4 match up. What happens if I subtract these equations from each other? And then see what results. So I'm going to take this equation and subtract this equation. When I take this true equation and I subtract this true equation, I get r plus s minus t equals 0. But wait a minute, that's this equation here. These are the same equations. Notice that to get this equation, all I did was use this equation, and these two together form this equation. That means that this equation depends on these two. So what happens is, I can forget about this equation. If I say, you know what, this equation's not important. I don't need it to be true. I'll forget about it. I will no longer make it be part of the requirements. I will no longer say that Tessa is as old as her brothers combined. I will remove that equation, yet it will still be true because the other 2 equations imply it. So these 2 equations being true implies that this equation is true. So this equation is dependent on these 2. It's not an independent new fact. So really, I told you 3 facts about these siblings, but I only told you 2 interesting facts. So there are 3 siblings, but 2 interesting facts. Therefore, there's some room to grow. That's essentially saying, if I told you 3 interesting facts, something that was, I told you something new, I'd be able to actually exactly tell you what the ages of the children are. However, I can't do that with the current set of equations. There's dependence, there's not enough information. I haven't told you enough. So this idea of what an equation being dependent means, and the fact that that gives me some room to grow, that's something we're going to learn about when we talk about Gaussian elimination. And specifically, this idea of doing arithmetic on equations by combining them in different ways, that's exactly what Gaussian elimination is doing. So this is going to help us discover more about the structure of our solution space, not just when we have a unique solution or we don't have a solution. We're going to learn about it by using this process.